pi r square, 7.5 centimeters square divided by 0.1 seconds. Okay, that's 10 to the minus 4. And we'll make that, so 25 into pi into 7.5 square into 10 to the minus 4 divided by 0.1. And this will be volts. Okay. So and this works out to 4.4 42 volts. So if you reduce this fairly strong field to 0 in 0.1 second, you can induce a 5 volt, 4.4 volts. Okay. If you reduce the same field in 60 seconds, all right, or in 1 second, the voltage induced would be 0.4 volts. Okay. In 100 seconds, it would be even, you just keep reducing the time. Where do you think this, why are we doing this? This is an induced problem. See, in an MRI machine, you see fields like that. And you just can't switch off the MRI machine just like that. You would induce currents in current loops, fairly high voltages, okay? So you want to quench a magnetic field slowly. If you have a strong magnetic field, you want to turn it off to 0 slowly, okay? So a single turn circular loop of wire of radius 50 millimeters lies in a plane perpendicular to a spatially uniform magnetic field. During a 0.1 second interval, the magnitude of the field increases uniformly from 200 to 300 millitesla. Determine the induced EMF in the loop. Okay. So here's a loop, and you're increasing the magnetic field from 200 to 300 millitesla, the radius of the loop. So the induced EMF is the change in magnetic flux over the time, and if the magnetic field is increasing, the induced EMF needs to produce a field in the opposite direction. So the induced direction is in this direction, okay, for an increasing magnetic field. All right, so the induced EMF is, you're changing the magnetic field times area divided by. So 100 millitesla pi r square, 5 centimeters, 0.05 meters square. So this is millis 10 minus 3 will make that 25 times 10 minus 4, and then 0.6. So this is 10 minus 6 volts pi 25 pi into 25. This is 78.5, and that's a microvolt. Okay. And so if the magnetic field is increasing, the induced current is in this direction, and the EMF around this loop is 78.5 microvolt. Okay, and if you know the resistance that is in this loop, you can calculate the current in this loop. All right, so here use Lenz's law to determine the direction of the induced current in each case. Okay, so if you move, so here the magnetic field is coming out of the sheet. If you move this wire in this direction, okay, the flux in this direction is decreasing. So what does Mr. Lenz say? The induced current is such that it opposes this change. So the current has to, since the flux in this direction is decreasing, you have to produce more flux in this direction. And so the current has to be in like that. So again, use your right hand, point your fingers in the direction of the current, and your thumb points in the direction of the magnetic field. Okay, so the induced current is in that direction. Okay, I'll just do a couple. So obviously in this case, the induced current is in the opposite direction. Okay. Here, what is happening here? So as you're bringing the ring in, the flux in this direction is increasing. Till what time does it increase, the flux?
Until the ring is fully in the field.
Right. So until the ring is fully in the field. So you induce a current only till this portion comes here. And once the ring is completely in the field, now the flux is not changing and you won't induce any current. Okay, so you're inducing a current until this guy reaches there, like that, okay? And since the flux is increasing in this direction, you want to produce a flux in the opposite direction. So the current, induced current, has to be like that. Okay, again, stick your fingers in the direction of the current and your thumb points in the direction of the field. Okay, so you want to induce a field in this direction. So the induced field is in the opposite direction. Okay. So B is increasing here. B is increasing here. So you want to induce a field in this direction, in the opposite direction. Induced field is in the opposite direction, and so the induced current is like that. Okay. And so on. Okay, so to me, okay, this looks like, okay, the way I read this is the field is coming out of the sheet, and this guy, the plane of the ring is parallel to the magnetic field, and you're moving it in this direction. So the flux is zero, and as you're moving this guy, the flux is not changing. There's no induced current in this situation. Okay? So what we're saying is the field is like this, and you're moving the loop parallel to the field. Okay? So there's no flux in here, which is not changing. Okay, this problem says a coil of 1,000 turns encloses an area of 25 centimeters square. It is rotated in 0.01 seconds from a position where its plane is perpendicular to the Earth's magnetic field to one where it's parallel to the field. Okay, so this is the initial state. And here's the final state. Okay, so right now the flux is N times B times area, and now the flux is zero. Okay, the flux, so initial flux is N times B times area, and the final flux is zero. Okay. If the strength of the field is that, what is the average induced EMF in the coil? Okay. So the EMF induced in the coil is delta phi. Okay. Okay, we'll just calculate the magnitude, delta T, NBA, or delta T. The final flux was 0, so final minus that, and then you take the absolute value. A 1,000 turns, 6 times 10 to the minus 5 Tesla. Area is 25 into 10 to the minus 4 meter square, and 10 to the minus 2 seconds. Okay, so this kills that. So it's 6 times 25, which is 150 times 10 to the minus 4. (15 millivolts). So the magnitude of the induced EMF is 15 millivolts. Okay. You see the induced EMF is quite small because of the Earth's magnetic field is quite weak. Okay. Okay, so this shows, so you move a metal rod, so the magnetic field is coming out of the plane of the paper, and you're moving it perpendicular to the plane of the, perpendicular to the magnetic field. Let's see what will be the direction of the polarity. If you have a positive charge moving in this direction, the force on the positive charge will be V cross B. V cross B, it'll move in this direction. So this end will become positive, and this end will become negative. And the voltage across this guy, across the rod, so the force on the positive charge is in this direction. The voltage is BLV, okay, where L is the length of the rod. Okay, so there's the magnetic field, there's the speed, and there's the length of the rod. So the voltage, induced voltage is 0.5 Tesla, 5 centimeters, and 8 meters per second. So you're moving the rod fairly fast. 8 meters per second is roughly how fast a person can run. Okay. Usain Bolt runs at 10 meters per second. So this is, okay, so we'll make this 5, that's 10 to the minus 1. So this is 25 times 8, which is 200 into 10 minus 3 volts, or 0.2 volts. Okay. So you take this metal rod, a 2-inch metal rod, and you move it in a 0.5 Tesla magnetic field, and it acts like a 0.2 volt battery. Okay. Okay, so in this problem, a 25 centimeter rod moves at 5 meters per second in a plane perpendicular to the magnetic field. So again, if you move, so in this, the magnetic field into the sheet of paper, V cross B, if you move the screw like that, it'll move in that direction. So this end will become positive, this end will be negative. Calculate the magnetic force on the electron in the rod. Okay. The magnetic force on the electron is Q V cross B. Okay. So if this were positive, on a positive charge, the force is in the upward direction. On a negative charge, the force will be in the downward direction. And the magnitude of the force is QVB, since V and B are perpendicular to each other. And so the force, the magnitude of the charge is, the magnitude of an electron's charge is 1.6 into 10 to the minus 19 coulombs. The velocity is 5 meters per second. And the magnetic field is 0.5 Tesla. Okay, so that's the force on this electron. This force might appear small, but the mass of the electron is 9.11 times 10 to the minus 31. So as soon as you start moving, all the electrons will collect here and the voltage will be seen almost instantaneously. Okay. The magnetic force on the electron, the electric field in the rod. Okay, so what happens is, so as you move the rod, electrons have collected here. This end has become positive. There's an electric field like that. And how many charges collect? Till the electric force on each charge is balancing the magnetic force. So Q times E equal to QVB. Okay. So the, so the electric field is V times B. The electric field in the rod is V is 5 meters per second. Okay, I put half a Tesla. The field is 0.25 Tesla. Volt per meter. So that's the electric field strength. Okay, and so this is convenient because if the rod is 1 meter, the voltage across the rod will be 1.25 volts. And if the rod is 2 meters, the voltage would be 2.5 volts and so on. Okay, the longer the rod, the greater the voltage you'll see. The potential difference between end of the battery, the voltage induced is BLV. (25 centimeter) and V is 5 meters per second. And again, the rod is a quarter of a meter, so the voltage should be induced should be a quarter of that. Okay. And that's what this should work out to. So this times that is 1.25 and a quarter of that, I guess. So and this indeed is a quarter of that. And then they ask you, what is the speed of the rod if the potential is 1 volt? Okay. So So when the speed was 5 meters per second, the voltage was 0.3 volts. You want 1 volt, so you got to go 3 times as fast. Okay? If you want 3 times the voltage. One volt, 0.25 Tesla, and L is 0.25 meters. You want 1 volt, so that is 4, and 4 times 4, that's 16. So 16 meters per second. Okay, so like we said, the voltage is 3 times as much, and you have to go about 3 times as fast, which is 16 meters per second. Okay, this problem says calculate the induced electric field in a 50-turn coil with a diameter of 15 centimeters that is placed in a spatially uniform magnetic field of strength half a Tesla, so that the face of the coil and the magnetic field are perpendicular. This magnetic field is reduced to 0 in 0.1 second. Again, so you can think of an MRI machine being turned off, and the magnetic field is reduced to 0 in 0.1 seconds. Assume the magnetic field is cylindrically symmetric with respect to the central axis of the coil. Again. Okay, so there's the magnetic field, and you're decreasing the magnetic field, so you're reducing it, and the induced field has to produce a field in that direction, so the induced current will be in this direction. Okay. So the induced EMF is delta phi over delta t. And the number of turns of coil, B times area. 50 turns, half a Tesla, pi r squared. So we'll make that 250 pi times 7.54. 250 pi into 7.5 square into 10 to the minus 4 volts. .42 volts. Okay. Okay, so here's a long solenoid, and let's say it's wound like that, and the current is flowing like so. If the current is flowing like that, then it produces inside the solenoid. So it's a cylinder with wires wound around it, and this magnetic field is inside the cylinder. And the magnetic field strength is given by, B is given by mu naught, N is the number of turns of wire per unit length times the current, okay? So they say the current through a long solenoid with N turns per meter and radius R is changing with time as di as that. Okay, so here's the magnetic field, and as you change the current, you're changing the magnetic field. Calculate the induced electric field as a function of distance R from the central axis of the solenoid, okay? So what we're going to do is we're going to calculate the electric field, okay, around this circle. So, and it's symmetric around the central axis. So the EMF is the electric field, line integral of the electric field, ds, and the electric field strength is constant, so it's 2 pi r. And the EMF is equal to rate of change of flux. Okay, so now we have to consider two situations. When the coil is inside the solenoid, and then when the coil is outside the solenoid. Okay, so as long as you're inside the solenoid, as you increase the radius, then the flux through that thing is increasing. But once you're outside the coil, now the flux is constant. Okay? And once the flux is constant, as you increase the radius, the electric field will decrease. Okay? So we have to consider two situations. So, and that's what this is. Calculate the electric field induced both inside and outside the solenoid. Okay? So, okay. R, we'll call the radius. So they give you the radius of this thing is R. Okay. For R less than R, E times 2 pi R is equal to d by dt, and we're just calculating the magnitude. The flux is, the flux through this thing is the magnetic field times the area. Magnetic field times pi r squared. And the magnetic field is given by this. So for R less than R, E times 2 pi R is equal to d by dt of mu naught n I pi r squared. Okay, so pi r cancels with that. You're left with 1 r, and then you divide it by 2. So it's mu naught n 2r di by dt. Okay, so that's the electric field. So what this expression is saying is the magnitude of the electric field increases as you increase R from the center. So you make a bigger and bigger circle. The electric field here is increasing. It increases till you get to the edge of the solenoid. Okay? Now you find the electric field for R greater than R. Now E times 2 pi r equal to d by dt of the flux, which is mu naught n I. Now the flux is, for a circle outside this thing, the flux is just the magnetic field times this area. That's the total flux. And as you make a bigger circle, the flux is not changing. Okay. So pi r squared. Now the flux is constant. Okay. So pi will cancel. Okay. And you get r in the denominator. So for r greater than r, the electric field is now mu naught n n r squared by 2r, r squared by 2r di by dt. Okay. So now the strength of the electric field falls off as 1 over r. So once you're outside the solenoid, the electric field now, its strength is decreasing as with r, inversely as r. Okay, it's falling off. So again, let me show you if magnetic field is increasing, the induced current is such that it wants to produce a magnetic field in that direction. So for an increasing magnetic field, the induced current is like so, okay? And its strength would increase till this point, and then once you're outside, it's decreasing from that point on. That's what we found, okay? And in part B, you can just put, for I, you put this functional form and calculate di by dt, and you get the electric field, okay? So put I equal to I naught sine omega t, and you'll get the electric field. This problem says the current in a long solenoid of radius 3 centimeters is varied with time at a rate of 2 amperes per second. A circular loop of wire of radius 5 centimeters. So this is a long solenoid of radius 3 centimeters. A circular loop of wire of radius 5 centimeters and resistor 2 ohms surrounds. Okay, so now you have a loop of wire of radius 5 centimeters. So you're outside the solenoid, and we'll be using this expression. Okay. So find the electric current induced in the loop. Okay. So the EMF for this loop, EMF is the electric field times 2 pi r. EMF times, this is the EMF, it's di by of this guy. Okay, this expression. So the EMF is d by dt mu naught n I pi r squared. Mu naught n pi r squared di by dt. So that's the only thing that's changing. The current in the solenoid is changing. Okay. And this is given to be 2 amperes per second. the rate of change of current is 2 amperes per second. So the induced EMF is mu naught. Mu naught is 4 pi into 10 to the minus 7 Tesla meter amp. Oh. Oh, they don't give you N in this problem, so we'll assume N to be, let's say, 1,000 turns per meter. So that's not given in the problem. We need that. Okay. Pi r is radius 3 centimeters. Di by dt is 2 amps per second. So that is the induced EMF in this loop. And then they give you the resistance of the loop to be 2 amps, and we can calculate the induced current. Okay, so let's grab this. Okay, so what is this? This is 10 to the minus 4, and you get 10 to the minus 1, so we'll make that 10 to the minus 8. 4 pi into pi into 3 square is 9 into 2. Okay. So, and this would be volts. .1 microvolts. And the current would be the induced EMF divided by the resistance, which is 7.1 microvolts divided by 2 ohms. That's the resistance, so it's 3.55 microamps. So what we are saying is, as the current in this solenoid changes at the rate of 2 amps per second, the induced current in this loop, which is sitting outside, is 3.55 microamps. In milliamp, you guys in labs were measuring milliamp currents. Okay, so this is 1,000 times smaller, the current. Okay. This problem says a flat square coil of 20 turns that has a side of length 15 centimeters is rotating in a magnetic field of strength 0.05 Tesla. If the maximum EMF produced in the coil is 30 millivolts, what is the angular velocity of the coil? Okay, so if you guys look at this expression, so as a coil turns, the amplitude of the voltage is that N times A times B omega. N is the number of turns of coil, A is the area of the coil, B is the magnetic field strength, and omega is the angular velocity. Okay. So the amplitude of the voltage is N times A times B times omega. So the angular velocity is the voltage amplitude divided by NAB. This is 30 millivolts and 20 turns, so this is 20. Area is, it's a square coil and the length is 15 centimeters. So 15 square into 10 to the minus 4 meters square. So that is the angular velocity. This would make that 10 to the power. So this is 10 minus 2. That would make it 10 minus 6. And that would make it 10 to the 3. So omega would be 30 into 10 to the 3. 20 into 15 square into 5, and this is omega is radians per second. Okay, 1 radian is about 60 degrees, so this is 90 degrees, a quarter of a circle per second. Okay. So that's the rate at which you're turning. All right.